So the next speaker is Dr. Hansa Rezac from the Institute of Organic Chemistry and Biochemistry in Prague in the Czech Republic. And you want to unmute and share your screen. You appear to be unmuted.
Yeah, I am working on sharing the screen.
Okay, looks good.
Hello, I would like to present my work I have done over the years on improving the description of non-covalent interactions in some empirical methods, mainly in PM6. And these methods are now implemented in MOPAC. My main goal is not the method development itself. We want to do some interesting calculations with the resulting method, and mainly in biochemistry, looking at protein-ligand interactions and in general large biomolecules. For this, it's really great to have very fast quantum mechanical code, and for us it's MOPAC with the great Mozyme algorithm that really makes it possible to calculate the whole protein in minutes, keeping the advantages of quantum mechanical calculations that don't need any system-specific parameters like molecular mechanics force fields. In these systems, non-covalent interactions are of really key importance, defining the structure of the biomolecule, its function. So having these described well is really crucial. And unfortunately, all the approximations that makes semi-empirical methods so fast make these described quite inaccurately. And when we discovered PM6, it had several features we were a long time looking for. So we started working on adapting it for our needs. It was around 2008. We quickly added dispersion correction analogously to DFTD. That was easy. What became more problematic are hydrogen bonds, which are underestimated by all the semi-empirical methods. Fortunately, they are underestimated quite systematically. So after looking at the results, it was obvious that adding some energy for each hydrogen bond in the system will get us very close to the reference results. And now the work was to turn this fixed energy term into a smooth potential that can be coupled to the method. And this eventually became the PM6-DH, the first method with both dispersion and hydrogen bonding corrections, published in 2009. And we didn't stop there, and not only but us, also others are working on this, and now there are many different approaches how to fix hydrogen bonds. The principal problem is the minimal basis set use in the semi-empirical methods, which doesn't provide polarization functions. So the response of the molecule to the very strong local electrostatic interaction is limited, and the strength of the interaction is underestimated. And among all the different approaches, the empirical corrections independent on the method itself are still the most successful ones, although they have some limitations as well. Over the time, we improved many aspects of this. So the current, but it's already 10 years old, method is the PM6-D3H4, which has the D3 dispersion developed by Stefan Grimme, and our hydrogen bonding correction, which is in principle a simple force field that is just added to the semi-empirical method. And it has no connection to the electronic structure. It is a closed formula calculated on the geometry, and the form defines the properties it has. And the H4 correction addresses several important things. We have exact gradient. It was not the case of one of the versions. It can handle proton transfer, what is very important. And in fact, it improves the description of proton transfer. The barrier height is also improved. It works for charge systems. It has smooth energy surface, and it does so with very few geometric parameters of the hydrogen bond. So it's quite simple. Then we move to other classes of interactions, mainly halogen bonds, which are the result of so-called sigma hole. It is the uneven distribution of the charge on the surface of the atom, if I can say this, where there is a positive region along the axis of the sigma bond, and it can interact with negative atoms. Fortunately, the theory itself at the level of MNDO or PM6 describes this electronic structure features well. What is missing is the parametrization of the rest of the method, which gives too strong interactions, too short contact distances, and this was corrected by another correction we called X. So in the end, it's PM6-D3H4X, and it adds the extra repulsion needed to keep the molecules at the right distance. The repulsion in general is difficult for semiempirical methods. It's not described really well by any of the existing methods, and it can be very important in some applications, especially if we start from imperfect geometries in a dense environment where some close contact can occur and can really spoil the results. This is the past. Now let's move to the present. As I mentioned, the PM6-D3H4X is around for a while, and recently we reparameterized it using new, much better, more diverse reference data. Jimmy has shown the BackDB website we started a long time ago, and now the new databases are hosted as this NCIatlas.org website. The new datasets feature sets covering different types of interactions with hundreds of systems, thousands of data points along dissociation curves, everything calculated with top-level computational chemistry. And it's a great resource for method development, and we took these data and updated all the corrections in PM6-D3H4, well, except dispersion where it was not needed. And it really improved the description of halogens. It improved the description of hydrogen bond that was previously biased because only few strong hydrogen bonds were used for the parametrization. So this is the current state of the art, which is quite nice, and we are actively using it in our applications. Here I can briefly show the results we get with evaluating the strength of protein-ligand interactions, what is very important potentially used in computer-aided drug design. This is a collection of 10 different proteins, each with a series of ligands, for which there are crystal structures and experimental binding energies. So we have the experiment reference. These are very complex systems, but we know that we are working with the right structures, and we have the energy we would like to reproduce. This is, of course, not only a calculation of interaction energy, but solvation has to be added and few more terms to get as close to the free energy of binding as possible. The solvation is covered by Cosmo, implemented in MOPAC, which is great, fast, and works for these large systems perfectly. And we achieve very nice correlation with the experiment. So it's about R squared is about 0.7, while the scoring functions which are used in docking and virtual screening perform much worse and usually fail in at least one of the systems we looked at, while our protocol based on PM6-DH4X works well even for the most difficult system. And this is a great showcase to demonstrate how much better it's compared to the force field. We repeated exactly the same calculations with Amber and GAF force field, and the correlation with experiment is really on the same structures. Everything is the same, but the force field can't describe the interactions as accurately as we would. So this looks really nice. We are working further on this, but by using it, we also uncovered many other limitations and issues. And that motivates us to work on new generation of methods. And the most important things to address are the repulsive contacts I mentioned already earlier. These are covered quite broadly in the new benchmark database. There is a data set of more than 700 different combination of molecules covering contacts between atoms of different elements, so we can have a pretty good view of what works and what doesn't. And this is a plot or a part of the plot of the final results for different semiempirical methods, where you can see that some interactions are described well, but some have some systematic bias. Usually the repulsion is underestimated, so it makes too strong interactions with too short contacts. And in cases like sulfur oxygen, sulfur nitrogen, this can get really serious, that the molecules almost fuse together, forming contacts that are close to the length of covalent bond, which shouldn't be there. And this is something we tried to address by reparametrizing the method using these reference data, but it didn't help much. And some of these issues are really connected with the limitations of the theory, with the approximations made in this kind of methods. Another problematic thing is the description of conformers of molecules or torsional profiles. Here this picture shows a data set of peptide conformers, peptides and small macrocycles, where on the x-axis there is error, and these are many methods. In yellow, it's DFT. And DFT, regardless of the functional basis set with dispersion correction, the errors are up to 1 kcal per mole, which is nice, useful in applications. But all the semi-empirical methods we tested here in blue have errors 3 times as large, and this is really not enough to find reliably the stable conformers of the molecule and work with that. And again, it is a thing that we tried different way how to approach it, and we haven't found a fix within the current framework of MNDO or PM6. And this led us to very recent exploration of the possibilities to address this by machine learning, because it's now the trend And not only that, it can actually work pretty well in this case because we are not developing new potential. We are looking for some local correction for something what already works quite well in most cases, and we have to correct only the small final bit of this. And we use existing large database that was developed for machine learning, connected with our own reference data. And here are the results. The problems with the conformers usually comes from some torsional profiles, and this shows how bad PM6 is. Black is the benchmark, coupled clusters. Blue is PM6-DH. It's really qualitatively wrong, having minima in wrong places, missing barriers. And these are simple organic molecules. This is biphenyl. And when we apply the machine learning correction, which was not parameterized specifically on torsions, but on some general conformers of hundreds of thousands of molecules, we get the red curve. It's in some cases almost perfect, and for sure it's qualitatively correct. The same applies to many other areas, including the conformers that were difficult non-covalent interactions. So here are different data sets we used for validation. It's part of the NCI Atlas data sets for non-covalent interactions, where, for example, the error in the repulsive contact is reduced from 3 to below 1. The conformers are described much better. This dataset, it's conformers of sugars, where the error is huge in PM6, get worse in PM6-DH4, and we get it really close to the DFT reference, which is here in green. So it solves many problems, and from the point of view how it works, it's mostly finished. We didn't found any problem where it would work worse than our previous correction, so it's we are only winning here. It's fast with some overhead, so it's it can easily work with thousands of atoms, but it will make a calculation of one water molecule relatively slower than without, because it requires initialization of a huge model. Now it covers quite useful chemical space, including sulfur, phosphorus, halogens, alkali metals, so it's actually usable, unlike some other similar methods that are already available, which cover, for example, the AIQM1 covers just the first 4 elements. So it's not enough for useful applications. And now we are the main work now, before this can be published and made available, is to interface this to MOPAC, because now it's in a state of kind of Frankenstein code that connects different pieces written in different programming languages, and we have to streamline that for all users. And in addition to development of this machine learning correction, we still plan to improve the method itself, because even though we have great machine learning correction, it's still difficult to correct errors which are too large. And many of these come from missing data in the parameterization of PM6. So there might be something with working name PM8, where we are adding more data to fix these errors. Here the bottleneck is the optimization tool. Jimmy mentioned the param program that comes with MOPAC. It's great, but it can handle few thousands of data points, and for this use we need working with hundreds of thousands. And right now we are developing a tool which will parallelize the optimization and use some advanced optimization algorithm that can hopefully handle that. So this is something that, if it works, can be done in the coming few years. So with these results, which we are really happy with, I'm quite confident that the future of semi-empirical calculations and MOPAC is quite bright. And I would like to thank my colleagues who helped with this, and the National Science Foundations for funding, and the Computing Center for providing the computer time we need a lot of. And thank you for your attention.
All right. Do we have any questions for the speaker? He ran a little bit long, so maybe we want to wait for the discussion section. But if there's time for maybe one quick question, if anyone has a question at the top of their minds.
Well, quick comment. I'm so pleased, Hans, that you are doing this. I have great hopes for the future of semi-empirical quantum chemistry.
Thanks.
All right. No other questions? Let's move on.